So we have this definition of an isomorphism, which is trying to capture the idea that two vector spaces have sort of the same vector space structure, essentially. Just as a note on terminology, we say that two vector spaces are isomorphic if there's some isomorphism between them. Typically, in fact always, there will be many isomorphisms between isomorphic vector spaces. So saying that two vector spaces are isomorphic isn't committing to any particular isomorphism between them. It's just saying that there is some isomorphism. But with this idea of isomorphism of vector spaces, this idea of isomorphism behaves very nicely. And what I mean by very nicely is actually that isomorphism classes, that is, collections of vector spaces that are all isomorphic to each other, actually form equivalence classes. So this relation of is isomorphic to is actually an equivalence relation. And remember, that means three things. That means the relationship should be reflexive, symmetric, and also transitive. So let's just check quickly why this relationship of is isomorphic to has each of these three properties. So first of all, for reflexivity, remember that this means that a relationship, I need a symbol, how about this? A relationship like this is reflexive if everything is in relation to itself, right? So in this case, is isomorphic to, what this would mean is that for every vector space, V is isomorphic to V. So is every vector space isomorphic to itself? Well, remember, to show that right now the only way we have of showing that two vector spaces are isomorphic is to explicitly write down an isomorphism between them. So how could we come up with an isomorphism between a vector space and itself when we don't know anything about the vector space? Well, actually, it's kind of easy, because there is a very nice function going from V to V called the identity function, usually written ID sub V. The subscript just tells you what the domain space is. And what this identity function does to a vector V is it just gives you V again. So clearly this is onto, because every output is an input. Clearly it's one-to-one, because if you have the same output coming out, that means you put the same thing in twice. So it's one-to-one and onto. And also clearly maybe not super clearly, but I don't know. I'm not sure if it's worth writing this down, but it preserves vector space structure, because if you have two vectors, right, the identity function applied to two vectors, well, by definition, the identity function just gives you what you put in. But by definition, V1 is the identity on V1, and then V2 is the identity on V2. So, and similarly for scalar products, so the identity function preserves structure. So this identity function is an isomorphism from V to itself, and so that means that this isomorphism relationship is reflexive. Right, so what about symmetry? Well, remember, symmetry means that if A is related to B, then B is related to A. So for vector spaces, for vector space isomorphism, this would mean if V is isomorphic to W, a vector space W, then W is isomorphic to V. So what we should do to prove this is suppose that, suppose that V is isomorphic to W. That means that there must be an isomorphism, so we'll write down an isomorphism F. Okay, well, we proved before that if you have an isomorphism, there is an inverse function for that isomorphism, and the inverse is an isomorphism. So this means that F inverse from W to V is also an isomorphism. But that means that W is isomorphic to V. And that shows symmetry. All right, finally for transitivity, remember, transitivity means if A is related to B and B is related to C, then A is related to C. So why is this true for, so the isomorphism version of this is if V is isomorphic to W and W is isomorphic to U, then V is isomorphic to U. All right, so that's what we need to prove. So we'll assume that V is isomorphic to W. In other words, we have an isomorphism from V to W. And also we're going to assume that W is isomorphic to U. So that means that we have an isomorphism from W to U. And we want to produce an isomorphism from V to U. Well, there's an obvious function lying around that goes from V to U, and that's G composed with F. So G composed with F is a function from V to U. Since F and G are both one-to-one, so is G composed with F. So there's a little detail there to check, but it's a good exercise. I'll let you check. Also, since F and G, this should be a G, since F and G are both onto, so is G composed with F. Again, that's a good exercise to show if you don't see why that is the case. So the main thing to show is that we need to show that G composed with F preserves structure. All right, so how can we show this? Remember, one way to show that a function preserves structure is just to show that it preserves linear combinations of just two vectors. So let's see what happens to G composed with F applied to a linear combination of two vectors from V. So this would be A1V1 plus A2V2. Okay. Well, G composed with F, just by definition, that's G of F of A1V1 plus A2V2. But we know that F preserves structure, so we can write this inside as A1F of V1 plus A2F of V2. But look, we know G preserves structure, so now we can use the fact that G preserves structure. We get A1G of F of V1 plus A2 times G of F of V2. And of course, this is A1 times the function G composed with F applied to V1 plus A2 times the function G composed with F of V2. And this shows, right, the fact that these two are equal, this shows that G composed with F preserves structure. And that was the last piece we needed. So now we know that G composed with F is an isomorphism. So V is isomorphic to U, right? Which is no big surprise, really. I mean, if these two vector spaces have the same structure and those two have the same structure, it seems like you ought to be able to chain these things together, and indeed you can, right? That's the content of transitivity. So these three properties, transitivity, symmetry, and reflexivity, show that this relationship of isomorphism really is an equivalence relationship.